Our next speaker is Carlos Tomei from Rio, and he's going to talk about other applications of factorization for solving flows. Please, Carlos.
Guys, don't worry. Only a fool would give a long lecture before lunch, right? So let's start with the basics. People said wonderful and deserved things about Jair, but I think I'm among the few ones who can report from the sublunar world, right? And it's all fine, also from that point of view. Jair has been a wonderful companion, colleague, friend, and I'm talking a very lato sensu interpretation of all those words, right? It's a matter of seeing how we relate to, I don't know, common friends, family, bicycles, right? The local, rather polemical sometimes, controversial sometimes, politics, and you've been a wonderful partner all those years. Really, infinite thanks. Okay, business. I'm presenting you two miniatures that you see. I'm not presenting a great project, nothing like that. I think it's two tricks. When I was preparing the lecture, I was reminded of no less a man than Atiyah, who once told me that he gives a lecture, he comes back 3 years later to the same department, and people say, "Oh, you gave this lecture, I remember, you talked about that," and it's just a small chunk of whatever he said, right? People always remember something different from what you expect. And indeed, here in Brazil, when kids, for example, have their birthday parties, right, everybody gets a little gift to take home, right, a small souvenir, right? So my intention is really provide you with a couple of souvenirs, okay? I would love if you people sort of had something to take with you. Okay, since it's two chunks, I, for the first time in my life, write a table of contents, okay? I'm going to tell you first this absolutely dishonest approach to history, right? I think that the Toda lattice was just staring at everybody in front of a Lie group in 1920s. Okay, I'll try to convince you of that. And once we stumble on the archetypical Toda lattice, I'm going to show you just this little extra trick out of which I got some mileage. And I think you guys should be more perceptive about it. Also because in a certain tradition, I'll be very concrete. I have no intention of putting it in the most general framework. Okay, this is something actually which should be taken into consideration. The second part of the story is related to an exquisite differential equation which was suggested in a paper by Tomei and Jair. And in that paper, they presented that equation. They found a number of conserved quantities. They presented numerical evidence that it should be integrable. And it turned out that in subsequent work, Lee and I showed that that was indeed the case. And some years later, also Tomei, Tudor, Jair, Marsden came up with yet another argument showing integrability. But actually, something I want to point out about this system is that there's a very cute way of generating a group, a finite matrix group from which you can do the usual yoga and get it. Okay? So it turns out that first I'll show you how Ren Chao, Lee, and I did it on loop groups, and then I'll show you how to bring it back to a decent matrix group. Okay, and apparently this taming of the group is something which is absolutely soft. You can probably do it at home with whatever your kitchen sink. So here goes. Again, I'm taking a very concrete example, okay? S is going to be a real symmetric matrix simple spectrum, and I'm going to consider the intersection of two orbits, an orbit by the orthogonal conjugation and by the upper triangular conjugation. This notation here represents matrices whose diagonal consists of positive numbers. Okay? Absolutely natural question. If you do the counting of dimensions, you might think that the intersection actually consists of a few points, but this turns out not to be the case. It's a very non-generic computation, and I'm doing it for you. Ooh, here. Okay, take someone in the intersection, okay, and now do the usual algebra, get rid of all the minus ones you see, and this equation here is telling you that S commutes with the product QR. Since S has simple spectrum, it turns out that actually the product QR ought to be a function of S, okay? If I write more on the slide, which I wasn't very willing to do, I might say that I'm interested actually in the connected component with the identity of this intersection, and by connectivity arguments, you wouldn't be surprised if I told you that actually your function might be interpreted this way here. Okay, so this is just connectivity. Now, let me tell you what this intersection is. Well, we saw it, right? The slice consists of conjugations of S by either, well, let me start again. Take this matrix here and write the QR, the composition of it. In other words, write it as a product of an orthogonal and an upper triangular matrix. Turns out that this is always feasible for an invertible matrix, and I'll use this notation here to denote the Q part of the factorization and the R part of the factorization. You might think that the notation is pedantic, but you see why I'm doing it. So it's clear, isn't it? You get the matrices intersection by performing exactly conjugations by the appropriate Q's and R, which you obtained out of this factorization here. So that's it. Actually, you have to be careful because, of course, if functions differ by a multiple of the identity, you exponentiate, everything trivializes. So this is not really where the action is. Okay? Now, the remarkable way, the absolutely trivial way of parameterizing this intersection is saying that why not look for flows inside of it? So what I do is I add here a time variable over this functional degree of freedom over here, you see. You might think that, well, how do you know that this indeed induces a flow, right? And I made some indication here that we should stop and think about it. But this is also one-liner in case, after those two lectures when I saw people reconquering the board, I'm on the verge of going to the board myself and doing the little piece of computation. But perhaps let's hold. Let's see if you have time in the end. You can always ask me if you care. So the upshot is that this evolution here actually can be phrased in two different terms, either by an orthogonal conjugation or by an upper triangular conjugation. Once you know that those things are flows, it's a Pavlovian reaction, right? You have to ask, what are the ODEs, right? And here's the Toda flow. Okay, there it is. So it's really that simple. Actually, it turns out that since there are two different interpretations of this evolution, you shouldn't be surprised that there are two different interpretations of the vector field itself, which, by the way, are trivially related. Okay? It's really that stupid. Instead of coming up with a very general context for that, what I'm going to do is show you in the second part of the talk how this is going to solve another example, okay, just for you to feel the flexibility of the argument. Instead, here I want to take a completely different track. I'm going to consider a second factorization, okay, which in good old GLN is actually the lower upper decomposition of matrices, okay? As you know well, everybody who teaches some baby linear algebra course has to go through this ordeal, right? You have to tell the kids that not every invertible matrix admits such factorization, right? And there are ways of characterizing the good matrices, but we don't really care. We are mathematicians. And now what I want to do is the following. I'm adding a new geometric ingredient here. A profile for a matrix is simply a staircase. For example, here's one profile. Okay? So Vprof actually is going to consist of the matrices which are 0 under this profile. If you're talking about symmetric matrices, of course, you have to think of a mirror version of this staircase over here, and you get zeros down here and zeros up here. Okay? Everybody's favorite profile. Well, unfair to talk about diagonal matrices, right? I'll try diagonal matrices, right? That's a choice, a very strict profile. In a sense, the first non-degenerate profiles when you search for coadjoint orbits of the triangular group, okay? But actually, we don't mind, as you shall see. So what I want to do now is the following. Choose a permutation and order the eigenvalues of your matrix S according to this permutation, okay? Think that you have chosen a matrix with a fixed spectrum and with a specified profile. Apply the spectral theorem to get the usual factorization, okay? Now comes the trick. Factor this matrix Q as an LU product, okay? Again, well, not every matrix admits such a factorization, and you see this mysterious object which I haven't defined actually means this. You're going to look at matrices S for which this factorization gives rise to an orthogonal matrix which admits an LU factorization. So that's the very indirect description of this object here, which is going to be actually an open dense set within this space here. Okay, notice that this, for all intents and purposes, it's an isospectral set in the sense that you fix spectrum, you consider all matrices with that spectrum with a specified profile. Okay? It's not a Lie group orbit, because once you intersect with the vector space Vprof, you're running into trouble. It's not even clear that this should be a manifold. Actually, it turns out that, for example, if S had double spectrum, that wouldn't be the case. But, well, since the early 80s, I had proven that in the triadiagonal profile, to say the least, this was indeed a manifold. And what I'm going to show you now is that actually manifolds are abundant. So one of the underlying themes of this short story is that this is a peculiar way of specifying charts to objects which in principle you should doubt that they are manifolds. I'll prove much more than they are manifolds. I'll come up with charts. Okay, as I was telling you, factor S, now factor Q, and transcribe what you learn about Q on that formula over here, okay? So far, I did essentially nothing algebraically. And I defined this new matrix here, which I obtained by taking the U's on this formula here to the other side. Okay? So what's left inside here is a matrix which I call B. And what I get, oops, that's a remnant. This is not an S, a T, this should be an S. Okay? And what I want to emphasize is the following. It's clear that this matrix here is lower triangular. Okay? On the other hand, this matrix here is a conjugation of a matrix with a given profile by an upper triangular matrix. So this conjugation also has the same profile. This fossil, which I didn't correct, actually was appropriate in the case of tridiagonal matrices. If your profile specified a tridiagonal matrix, then this conjugation here would be what a numerical analyst would call upper Hessenberg. But I'm doing something more general now, okay? What I'm saying is that if you choose a profile and you conjugate by something upper triangular, you don't lose the zeros you have under the staircase. So the upshot is the following. This matrix here is lower triangular. It respects the profile, and more than that, of course, it has the eigenvalues along the diagonal because this is a conjugation by something lower. Okay? And now, let me tell you what the upshot is. The isospectral manifold is covered by those open dense sets. There's one such dense set for each permutation matrix. And within each such domain, the map which goes from S to the lower part, the strictly lower part of B, is a diffeomorphism to some Rn. Okay? Notice that this n here, of course, depends on the number of animals you see here above the staircase. The really lucky break, however, is this one. It turns out that for B variables, okay, or at least for what you see of B below the diagonal, you get the simplest possible evolution if you try to evolve your original matrix to the Toda flow. Okay? So this is indeed the change of variables which makes Toda looks linear. Okay? Now, let me show you what that boils down to in the case of tridiagonal matrices. Let me remind you of what people used to do before B coordinates. Well, people used to hang around tridiagonal matrices, and Moser used to parameterize Jacobi matrices, which are tridiagonal symmetric matrices with strictly positive subdiagonals, by looking at the first coordinates of the eigenvectors. It turns out that Jacobi matrices always have simple spectrum, and you can always choose the first coordinates of each eigenvector to be strictly positive numbers. In particular, that made Moser very happy because that made clear that such quadrant, positive quadrant of the unit sphere actually was isomorphic, of course, to nRn-1, and that was a parameterization of the Liouville-Arnold torus for the Toda flows. But you see what the rub is. It turns out that most of the interesting dynamics related to those problems have asymptotic limits which are not Jacobi matrices. In particular, you're constantly hitting diagonal matrices. And unfortunately, those coordinates here, they don't reach the diagonal matrices. So that's why I was emphatic about stating that, okay, now we have coordinates which convert any asymptotic questions into local theory. Okay? And as I'll show you, you can do stuff with that. Well, let me repeat one of my favorite pictures. Well, this is the 3x3 case, tridiagonal matrices with eigenvalues 8, 4, 2. The interior of this hexagon here consists exactly of the Jacobi matrices. Notice that this is not exactly what you think of R2, right? It turns out that when you go to the boundary, you get this very peculiar closure, which, by the way, is indication that those coordinates here become wildly singular. Okay? On the other hand, if you look at, as I was telling, those were just Jacobi matrices which have two positive subdiagonal entries. It turns out that you have 4 different choices of signs for those 2 entries which correspond to those 4 hexagons in the picture here. Notice, by the way, that this is indeed a hexagon. Count it, count it. Notice, by the way, that the very center of this picture is a diagonal matrix, 7, 4, 5. What this picture is showing you is actually one of the domains of one of the charts for B. So what I'm stating is the following. instead of using W's to parameterize over here, you might use B's to parameterize over those 4 guys over here. In particular, of course, this diagonal matrix is smack in the center of your coordinate system. Okay? And, well, fair enough, this guy here is, again, a copy of R2. Okay? So it suffices to look at those few numbers you obtain in the subdiagonal of the matrix B, and those guys here are much more well-behaved coordinate systems than the standard norming constants. By the way, they turned out to be very closely related in algebraic terms. Look at that. At least in the tridiagonal case, because keep in mind, once you go beyond tridiagonals, you don't even have decent norming constants. Okay? That was yet another story. But in the tridiagonal case, what I'm telling you is that you go from standard norming constants to the new B coordinates by essentially taking quotients. What this formula is telling you, and by the way, these are just conserved quantities, right? They are the eigenvalues of the matrix. So what this is telling you is that the W's, the quotients of W's are more well-behaved than the W's themselves. Okay? There's some regularization by taking those quotients. Okay? For example, this limit here works over here in the very center of the chart. That wouldn't make sense at all if you look in W variables. Okay? Okay. Let me get back to a comparison of the 3x3 case and the 4x4 case, which are another one of those pictures which I love to have in my pocket. And I'm going to use part of the story to sort of maximize memory, right? It turned out that in the early 80s, I had this conversation with Tony, which visited me at Yale at the time, and I had told him that indeed I had proven that the closure of Jacobi matrices was isomorphic, homeomorphic actually, to the convex closure of certain very special points, which are the diagonal matrices obtained by permuting the eigenvalues in all possible ways. So the reason why those pictures are here is that now you can see that this is a hexagon because it has 3 factorial vertices, and this is whatever it should be because it has 4 factorial vertices. Okay? Well, and Tony immediately reacted in the right way, right? A convex polytope. This should be the image of a momentum map, right? And it takes more than 2 momenta, right? Something like 5 years later, it turned out that Tony, Tudor, and Herman had obtained a specific description of this correspondence here in terms of a momentum map. There it is. You start with a Jacobi matrix. You again use the spectral theorem. Out of the blue, you flip the order of those 2 matrices here and consider the diagonal of this product. Beautiful example of dressing. And actually, the argument is incredibly slick. It uses all kinds of tricks, not only related to the Toda flow, but not with Guillemin-Sternberg approach, but with Attia's approach to the convexity of the momentum map. I remember, Tudor, you came here, possibly in this very auditorium, and gave a lecture on that. I introduced you, and I said, now, guys, you're going to hear the most complicated theorem in linear algebra. I had no idea of anything getting closer to the proof of that. And actually, I sort of was very intrigued by the fact that, okay, I could do that with sort of bare hands, okay, and the guys came with an explicit map. But once you have an explicit map, it should be simpler to do things, right? And indeed, I'm happy to report that at this point, after the PhD thesis of a student of mine, Ricardo Leite, we have really something that an engineering student can understand. And by the way, now that we have B coordinates, we have an even simpler description of what's going on, right? So strictly speaking, you should think that those B coordinates provide an algebraic description of the integral of this fascinating polyhedral, okay? It takes the positive quadrant of our n to the interior of such polyhedra in algebraic terms, essentially. Okay. Turns out that once you can look close to any diagonal matrix you want, you can compute, for example, wave maps or scattering maps for the Toda, which were computed originally by Moser, with a sleight of your hand. Okay? You just change variables from what's going on to the diagonal at minus infinity, from the diagonal to minus infinity, at minus infinity, to the diagonal at plus infinity. So now it really became, this computation became a triviality. Turned out also that now that we know so well what's going on close to the identity, we can do something which is much more delicate, which is the following. Actually, I was talking to you, Tony, the other day. I always have the impression that we complete integrabilists sometimes curse our own equations, right? Someone comes to you and says, I have this set of equations. And then someone says, it's completely integrable, and never talk to it again, right? And it turns out that, no, on the contrary, how nice, it's completely integrable. We should do something about it, right? And actually, numerical analysts have this spectacular source of examples, because a number of numerical analysts associated to computing spectrum, they are indeed discrete versions of integrable systems. But it's not that you choose an initial condition and you let it flow until the end of the universe. What a numerical analyst does is the following. He does an iteration, and he says, now I know a little bit more about my matrix than I used to know before. So I'm going to choose another integrable system within the same family of commuting maps. So what they see all the time in real life is not the usual, I should call Richard to help the whole class doing periodic evolutions on a torus, right? Instead of that, what you should think is that you flow for 1 second, then you make a little correction on your route, okay? Then you move a little bit, then you move a little bit again, okay? And what you have to do is dynamics, this continuous dynamics on this family of integrable systems. Turns out actually that Cantor sets appears, I mean, there's a whole series of new phenomena associated to work that Nicolau, Ricardo, and I have been doing in recent years. More than that, since I keep telling you that norming constants are not as sturdy as B coordinates, right? Of course, you should consider this as a possibility of new numerics, especially inverse variables numeric, right? You want to reconstruct something out of such variables. Well, this is yet another tradition, even in the discrete case, right? People used to, for a long time, the Bohr-Golub algorithm to go from norming constants to Jacobi matrices. And then Greg and Herod came up with this Ruthishauser-Kahan-Paul-Walker algorithm, which to my utter surprise was exactly what we needed. It's the usual business, right? You think that you invented the wheel and you're going to show something new to the numerical analysts. They've been there for 40 years. They have no idea why they should do it that way, okay? But they did it, it worked better, they were very happy, right? So there was no debate about why that should be, how should I say, a polemical algorithm. It turns out actually that the B coordinates are exactly the theoretical setup to understand this algorithm over here. But it turns out that now there's actually a possibility of going 1 step ahead of those guys. Once you realize that those data are dependent on the chart you choose, you have an extra degree of freedom. Okay? You are entitled to choose a chart in such a way that the data you gave is closest as possible to a diagonal entry, okay? And this, if you think about it, is exactly what you do when you do pivoting when solving a linear system, right? You're just using the permutation group acting on GON to obtain more stable approaches to the LU factorization. So this is numerical work in progress. Okay, end of the first story. Any question before I go on? Or we might as well postpone in case we have extra time in the end, okay? They are new manifolds, indeed. Those coordinates broke the tridiagonal barrier, okay? We can write down flows in those coordinates. Actually, let me give you sort of a holy grail to the whole story. Again, if I give you a tridiagonal, if I give a numerical analyst a tridiagonal matrix and you ask him to compute the eigenvalues of such matrix, he would love to have a divide and conquer algorithm, which, by the way, is available nowadays. All the methods associated to integrability instead are only able to start generating zeros in the subdiagonal, on the subdiagonal at the very bottom of the matrix. You don't know how to slice. You only eat it from a corner. Okay, this is what a numerical analyst would call deflation. Right? Turns out that whenever you want to do something that your pictures are telling you to do, you cannot do it algebraically. The computations are incredibly hard. So actually, what I'm looking is for the possibility of new algebra. You see, for new, literally new ways of computing things. In particular, if I could get different flows, for example, I'd be happy. Those, actually, the integrability of the Toda animals by now is completely off the point, in a sense. In this perspective, symplecticity is a red herring. First of all, we all know that you're not entitled to approach something, right, because of conservation of volume of phase space. However, what I'm telling you is that, listen, we linearized all those maps out of nothing, right? We didn't have to use additional structure. It's something different that's going on here. It's somehow the coexistence of those two factorizations from the very beginning. If you want to take the theoretical route, okay, it's up for grabs, okay? But there's so much actually to consider. For example, profiles are stratified by coadjoint orbits. Okay? If you try to pick those Casimirs one by one explicitly, we'll never meet again. Okay? That's one of the reasons why people cannot prove that Toda is integrable on an arbitrary coadjoint orbit. It's easy to do it on tridiagonals. You can do it on full orbits, okay? But try to get something in between and you're lost, okay? And this is sort of a cynical approach to it. Stop talking coadjoint, okay? Perhaps look at those larger, those packages of coadjoint orbits, which, by the way, form a vector space, right? And you'll be happy again, right? I wonder. Okay. This equation here is known to the Greeks, okay? His n is a constant. You know how to exponentiate this. Here it goes, okay? Of course, don't underestimate, right? If you're doing standard quantum mechanics and you do this in infinite dimensions, it's not that simple, okay? But we're playing matrices. So Bloch-Iserles instead considered this equation here. Replace s by ns squared. Which, by the way, is not a Lex pair in the sense that you don't have s prime s, you have s prime s squared. But they immediately wrote it this way here. Turns out that this is equivalent to this, and now you have a Lex pair formalism. Actually, they went one step beyond, and they wrote it like this. Think that there's a loose parameter z over here, okay, and think of this polynomial, matrix polynomial here, evolving. And it turns out that this is equivalent to this equation with the statement that n is indeed constant. Why is this nicer? Because what this is saying is that because you have a Lex pair structuring of your original equation, not only the eigenvalues of s stay put with evolution, but the eigenvalues of this expression here for an arbitrary choice of z. So that means that you found many more conserved quantities. Okay? Great trick by Manakov, right? Well, the upshot is that you have a gazillion conserved quantities, right? And integrability is shouting at you. And indeed, what they proved in that original paper was that those equations were indeed within a context of Poisson geometry, and they did numerics to show that orbits were winding around God knows where, okay? Well, so Luenchai and I had a look at this, and essentially what I have to report is the following. The original equation can be interpreted like that. You see, this is a symmetric expression on matrices n and s, where you use one n and one s. Here is all possible symmetric monomials you can form out of s and n, where you use 2 copies of s and 0 copies of n. Okay? It's unavoidable to think of symmetric expressions because you are computing s plus zn and very different traces of those powers, right? So you wouldn't be surprised if I told you that actually those 2 representations of the original equation fit within a much larger box, which consists of those expressions of that kind here, which, by the way, are indeed the extra conserved quantities in a sense. They should be related to the extra conserved quantities that were obtained with the Markov trick. Okay. Of course, what do you want to do in life? You want to think of this as being, of those equations here, and being a Lex pair for an appropriate strange animal here, something which will play the role of a skew-symmetric matrix. And of course, that's Pavlovian too, okay? Not the Greeks, but some monks in the 15th century have done that at some point. So it was a matter of finding the right animal. And I'll be rather brief here because, again, what I want to point out is sort of an offshoot of whatever's going on here. So the trick is the following. You consider this infinite dimensional group of loops, which are maps from the circle to invertible matrices with certain specific symmetries. Okay? Now, an open-dense set of such groups had big factorizations of the form. You see, you have functions of matrices defined on the circle. What this is requesting is you being able to write such functions as being a product of 2 functions, one which has an analytic continuation inwards and one having a continuation outwards. This is the so-called Riemann-Hilbert factorization. It turns out actually that this is pretty much LU within this context, okay? This is so LU, but so LU that I would love to tell you that what B coordinates do when you do inverse theory is really discrete Riemann-Hilbert. And yeah, there is, of course, this is not a theorem, right? This is just an analogy. There are 2 columns with different statements, okay? And actually there's more than meets the eye. Well, again, pick any G here, factor it like that, and here comes the semi-direct, the object which Toda identified as a semi-direct product, right? G times H is an expression like that. Once you have a group, you get an algebra. Once you have an algebra, you have, you first need a coupling before I dribble and state that, now I have a dually algebra, right? And the coupling, again, is something which looks a lot like a natural object, especially if you've seen that for 20 years, right? You have loops, you have complex functions, you're trying to compute products and getting a residue. Okay, this is non-degenerate, everything works. And now the lucky break has to do with the fact that you look at a very simple coadjoint orbit, which is this one here. Pick a symmetric matrix S0, which was the initial condition for the Bloch-Iserles equation. Look at N0, which was that constant, and consider what's the coadjoint orbit passing through this point over here. Okay? Here it is. In other words, you grind, you get the Casimirs, everything counts fine. You have, of course, a symplectic structure over there. And here comes the unavoidable theorem, which states that if you look at those Hamiltonians here, you obtain the answer to the question I left behind. In other words, you finally found, you found from the loop group point of view, a symplectic interpretation to the Bloch-Iserles equation. Okay, here it is. And of course, the lucky break is that if you want now, you can solve those equations in terms of factorizations again. In that case, by the way, the Riemann-Hilbert problem can be solved in terms of theta functions of the natural underlying Riemann surface. Now comes the part of the story that I would like to emphasize. Notice, by the way, that I'm done. Huh? It's working. The fact is that your original orbit was very small, right? It was just a collection of matrices of that form here, satisfying a few Casimirs, okay? So the orbit itself is finite dimensional, first observation. The second has to do with the fact that all the computations we have to perform to compute this coadjoint orbit here actually are only performed up to second order. In other words, you don't notice whatever is happening when you conjugate by loops of the form identity plus something of third order. By the way, why is minus 3? Because I want to extend to infinity, right? 1 over z type stuff. So what this is telling you, and this is the stupid remark I want to make, is that you don't need the full loop group, right? You should think that guys like that actually, form a normal group. And again, Pavlovianly, you pass a quotient. In other words, everything you need to do to get symplecticity, algebraic environment, and the like is happening on a finite dimensional group, the quotient of the huge loop group by this huge normal group here. Okay? At that point, of course, you have the right of saying, okay, it's a finite dimensional group, but it's still not a matrix group. Okay? Well, here it is. Now it's incarnated as a matrix group. Who'd say, right? If you look at the set of all matrices like that, those are n by n matrices. Those are identities. Those are symmetric matrices. This is Q-symmetric. All matrices of this form, they do form a group. And if you look at its coadjoint algebra, you find exactly the orbit in which the Bloch-Iserles problem is being solved. You could wonder, what kind of macumba is this which generates this guy? Again, it's sheer pencil pushing. What do? Well, you think that a loop is actually x by multiplication, right? And instead of thinking it this way, you go into Fourier variables, right? In other words, multiplication becomes convolution by matrices which are constant along subdiagonals, right? Toeplitz-like. On the other hand, since your original loop had an analytic continuation at minus infinity, it only has frequencies on one side. This justifies the zeros below the diagonal. So the upshot is the following. What you're seeing here is simply what you get when you think of all guys in LG minus, which consists of upper triangular matrices written in Fourier variables, which give rise to convolution, and modded out by cubic tails, which is what the quotient does, right? You'll be left with just algebra, which goes up to second order, which is exactly what I was telling you before. Thanks, everybody.
Thank you.